Hello everyone. We're starting a free open lecture in our Discord channel. All our lectures are held daily without breaks. If you're a viewer and want to ask questions and get answers in an online format, then join our lectures. You can find the link to Discord in our Telegram channel. To find out the time of the lecture, join our Telegram channel and Discord. The first task of Rudolf Jolocek. So what's the essence of the task? Let's get right to it. 2 seconds, 256 megabytes. We have identical triangles, absolutely identical. And so Rudolph decided to draw some kind of Christmas tree from them. Here's an example of such a Christmas tree. So here we have a base of 4. This is absolutely h2 is the height of this triangle. And then we have the coordinates 1, 4, and 5, which are exactly where the base is located. What do we need to output? I think you can guess. We need to find the area of our Christmas tree, meaning the area of all these figures combined together. The restriction we have is that the number of branches on the tree is between approximately 2 and 10 to the power of 5 at most. The same goes for the height and base of the triangles and their overall dimensions. Next, we have n heights at which the base is located, up to 10 to the power of 9. But this is the number of tests, which is 10 to the power of 4. As usual, the sum of n across all input data does not exceed 2 times 10 to the power of 5. Since our task is in floating point numbers, because that can happen, it's important that the absolute or relative error does not exceed 10 to the power of 6. One more time, the test cases aren't really that important to us, because we still have a limit of 2 times 10 to the power of 5 for nd, where d is the base, and h is less than or equal to 2 times 10 to the power of 5. Nyy is less than 10 to the power of 9. Sorting is not required. They are all arranged in order of growth. That is, from smaller to larger, everything is normal. If you feel like sorting them, you don't need to. And the error limit is approximately no more than 10 to the power of 6, which is denoted as the delta in the answer. I'll write it like this for clarity and understanding. Less than 10 to the power of 6. Let's go. I think everyone knows how to say the area of a triangle. We have a base d and a height h. They're always isosceles here, right? And they are always positioned exactly on the same axis. This is a beautiful and festive Christmas tree. They are all quite similar. They are all absolutely identical in appearance, and they always go straight along the y-axis, standing tall and proud. I think this is the y-axis. I sometimes get it mixed up. Well, yes, it's the base multiplied by the height and divided by 2, that's all correct. But we have a problem. If we do it this way, cleanly, then in the case of intersections we have... Of course, they will certainly break. We definitely need to do something about this. How can we absolutely resolve this? We indeed have overlaps. We know their heights. We know one of the bases. We know the heights because we have y. That is, here we have y4, here y5. So, let's take it straight from the example. So we have n3d, which is a complex structure with a height that measures 4 units, and the heights are specifically 2 and 1. Well, for 1, 4 and 5 are located at 1, and it fits perfectly and completely because 1 plus 2 equals 3, so we count it fully. But here, in this scenario, they overlap with one another in this particular instance. How do we determine the precise area of all this stuff somehow? In a logical way? Well, yes. If the difference between the upper and lower values is less than the given height measurement, then we can conclude that an intersection is occurring. So we need to do something with this FSP. Alright, actually calculating trapezoids is good and all, but we have a much simpler solution. Alright, I won't torture this. So what's the point? We're actually going to keep everything as simple as possible. We're just going to remember the height of the previous triangle. We'll need that, just in case. Well, it's clear that in the first case, when we read the first triangle, this height will be equal to like -1, right? And we'll just simply know that -1 is an obviously illegitimate height, so we don't need to compare with it, as we can clearly see. But comparing, if it fits, then everything's fine. We're adding it to our answer. Well, a triangle. The triangle, in short, is whole. Then we move on to the second stage. Here the height is perfectly suitable, as you can clearly see, quite obviously. So we add the triangle to the answer again. But this isn't a triangle, it's a trapezoid. But actually, in fact, we're not too concerned about that at this stage because we're moving on to the next step at all. Look, here the height is actually different. It's smaller. The difference between X and Y is less than the height. So what do? We're actually adding the triangle again in response because, well, we're adding it anyway, but we're also subtracting a smaller triangle from it. This one here, because we've already calculated it. How are we going to find it? Well, it's very simple. Actually, we can get our remaining height. I'll call it delta H. Well, how do we do that? Got it. Just simply subtract the difference U from the value of H. We'll ultimately get our delta H right there, and therefore the ratio of dH to H will be equal to the ratio of dd, or they refer to it as delta D, which is sometimes abbreviated as D to D. In this context, we are already familiar with the numbers 1, 2, and 3, which are essential components of the concept. So, we'll be able to find the base of this triangle. We will find out the base of this triangle. And we have D and DH as variables in our equation, which are crucial components. We multiply them again, divide by 2, and subtract all of this from the solution. Well, the code for the solution is pretty simple, but again, it's important because we have a very crucial adjustment. We're not working with floats because floats aren't accurate. We're at least working with doubles, but since we have this fantastic long double, yeah, it varies across compilers, but it's definitely not less than double anywhere. So, we just use long double, and that's it. Everything works great. In Python, well, you see for yourself whether you need decimal or not. Probably you do, but it's not a sure thing. And actually, again, pointless filler. We don't look at it. We read NSH. Just so you know, previous here is -1 for this check, starting at 0, and we just read Y. It's clear that if this is the only exception, we just add it. Otherwise, we do this check. If it fits, we just add it. If it doesn't fit, I didn't bother writing delta H10. Here, I'm looking for the base t's. How to find it, I've already said. And we add and subtract everything after which we output. And to output with the needed precision, I specify count.precision here. You could also set count.precision here to make it work properly. Whole point is prestigious. Could set.
Want to become a great programmer? Subscribe to our Telegram channel.